So I was planning to say more, but so let me start by now splitting the blackboard in two. So here I will have something which has to deal with the generic complex algebraic geometry, and here with like is random. Okay. So what I want to discuss now, which is what I wanted to do in the morning, it is this existence of a ring structure where these random computations are happening. Okay. So let me start maybe. See, like just to motivate and explain, if you intersect generic hypersurfaces Z1, Zn in Pn, the number of points of intersections is d1 times dn, right? And this is just Bezout. And now we have seen like this result by Edelman, Kosan, and Schuben-Smail. And if you count the expectation of the number of point of intersections, this is like in the Bombieri-Weil case, over the reals, you're going to have d1 times dn to the 1/2. Okay, so this is what you have seen. So one thing which is interesting about the Bezout computation is that this number actually it's computed in the cohomology ring of the complex projective space. So this computation happens in H star CPN with coefficient in Z. So you apply like if they intersect transversely, and this is true for like the generic choice, this number here is the number of points in the intersection. You apply Poincare duality, and Poincare duality transforms intersection product into cap product. Then the Poincare dual of an hypersurface of degree d, it's d times the Poincare dual of an hyperplane. You use the fact that in the cohomology of the projective space, it's a ring, so the degrees come out, and then you just have to intersect n copies of an hyperplane, and they intersect at one point. Okay, so this is what's happening. But it doesn't look like anything like this is happening here. Certainly, it's not happening in a cohomology ring. Because, well, first of all, the answer, it's not an integer. Okay, that's what we know. And I mean, some of these hypersurfaces might even be empty with some probability. Okay, so there, if anything is happening, it's not a cohomology ring. Okay. Here is another example that I like a lot. So this would be example 1. So pick lines L1, L4. These are lines in CP3. And you might ask, so how many lines? How many lines intersect L1, L4? Okay. So here you're asking how many points. Here's how many lines. Okay. So how many lines intersect 4 generic lines in CP3? How do we study this problem? Well, I take omega L. This would be the set of lines hitting L. Okay, this is a subset of the Grassmannian of lines in P3. It's actually called a Schubert variety. It's a cycle with coefficients in Z of codimension 1. And what we're asking is how many points are there in the generic intersection. Okay, so it's the same type of computation, except that now it's not happening in the cohomology of CPN, but it's happening in the cohomology ring of the Grassmannian. Okay? And computing in this ring, it's what it's called Schubert calculus. And the answer, which is computed using this Schubert, is 2, just 2. Okay? So like these things generically intersect in cohomologically 2 times the class of a point. So the number of points of intersection is 2. So this number 2, how do you get it? Using Schubert calculus. Okay? So that's another story. But of course, and this is what I tell you, there are configurations of real lines for which there is no point of intersection. And these configurations are stable. Okay, so you perturb a little bit the lines, then still you get no point of intersection. And Schubert calculus also works over the reals, but you have to work with Z2 coefficients. And just tells that the number of lines intersecting 4 generic lines in RP3, it's even, number of real lines. So it doesn't say much. But see, these lines now, instead of letting them be generic in CP3, you can take L1, L4, these random lines. This means that I'm sampling each one of them from the Grassmannian of lines in P3 with the uniform distribution. Okay, that's the only invariant distribution. And you can ask for the expectation of the number of lines hitting L1, L2, okay, L4. Okay, it's a perfectly phrased problem. So essentially here, the parameter space, if we want to really go back to our problem, would be like 4 copies of the Grassmannian of lines. Every point in this parameter corresponds to a configuration of these 4 lines, and we are integrating the function number of real solutions to this problem. Okay? And we know that this function takes generically either the value 0 or 2. And so you can write it down. And here is the starting point. So with Peter Burgiser, we observe that this number is 4 factorial times the volume of some convex body, which sits inside the space of matrices, which is the tangent space to the Grassmannian at one point. You might object that every number, positive number, is the volume of a convex body. So in this identity, as I wrote it now, there is nothing at this point. Because, do you agree? If you tell me the number is 1.7, which is about what is this number, just take a convex body of volume 1.7 divided by 4 factorial. Okay, so that it's obvious. But there is a little bit more here, so which is what I want to explain. This convex body, it has some explicit description, actually. It is a tensor product of balls. It's already something more. But the thing that I want to explain is this fact that so volume is the polarization of a multilinear form on the space of convex bodies, which is mixed volume, which is multilinear, as I said. And when you do the cup product here, that's also something which is multilinear. So it's linear in each argument. Okay, so this seems to suggest that there might be something like a volume, like a ring structure. After all, that's the same story happening here. Like in each of the hypersurface, this formula is linear in each of the hypersurface, if you think, like it's multiplicative, okay? Okay, so question, is there a ring where the right-hand side is happening? The answer is yes, and is what I want to explain. And it's a ring where the elements are convex bodies, but a special type of convex bodies, okay? So the elements of this ring, before I tell you the ring structure, let me just tell you what are the elements, are zonoids. So zonoids are limits in the Hausdorff metric of Minkowski sums of segments. In other words, if you have 2 segments, which are convex bodies, after all, very special type, you can take their Minkowski sum. And this, in this case, would give this segment, this convex body. Okay? So now this operation of iteratively taking Minkowski sum of segments, it's not close with respect to the Hausdorff metric on the space of convex bodies. So for instance, if you start taking this segment, plus this segment, plus this segment, plus this segment, plus this segment, and so on, okay, and you divide by 1 over the number of segments you have chosen, and you let n go to infinity, you don't get the sum of segment. You get the disk. Okay? So the set of convex bodies which are Minkowski sum of segments, it's not closed under the Hausdorff metric. Okay? The Hausdorff metric is some metric that you take on the space of convex bodies, a very natural metric. Or cultural, depending on... Okay? The closure of the set of Minkowski sum of segments is the set of zonoids. By the way, the Minkowski sum of segments, they have a name themselves. They're called zonotopes. Okay, so zonotopes are Minkowski sum of segments. You take the closure of the set of zonotopes in the set of convex bodies, you get zonoids. Okay? They're quite interesting objects. So for instance, a convex body is a zonoid in 2 dimensions, if and only if it's centrally symmetric. In 3 dimensions, much more hard to detect whether it's a zonoid, and there is no local characterization. A polytope is a zonoid if and only if all of its faces are centrally symmetric. But a convex body, it's more difficult. So Weil gave an example of a convex body with the property that at every point there is a neighborhood of this point where it coincides with a zonoid, but is not globally a zonoid. Okay, so that's, in fact, centrally symmetric convex bodies, you know that they correspond to norms. Okay, and a convex body is a zonoid if and only if the corresponding norm it endows the space with the metric induced by some L1. Okay, so take a vector space with a norm induced by a zonoid, okay, by a convex body, sorry. This convex body is a zonoid if and only if this vector space is isometric to some subspace of L1. Okay, it's difficult, but interesting, the interesting type of objects. So I denote by Z of V the set of zonoids in V.
Does it mean that zonoids are linear sections of?
Linear sections of L1, yes, of L1. But L1 in infinite dimension, okay, not the small L1. So you see, this it's closed by Minkowski addition. That's just because Minkowski addition preserves this property. But of course, we don't have the, I mean, it's not even, I want to turn this set into a ring, but it's not even an additive group, right? There is no negative element. Well, that's easy. You can just take formal differences. Okay, so if instead of looking at zonoids in V, I take formal differences, that's not a problem. So immediately, if I take the Grothendieck constructions, that's the object I'm looking at. And another thing that is convenient in this setting is to center these convex bodies to be centered at the origin. They are centrally symmetric, so just for simplicity, we just translate them back to the origin. Good. Now comes the ring structure. And this is something that we introduced with Peter Burgisser, Paul Briding, and Leo Matis, who is here in the audience. So let me denote by A of V. This is the following. I take the direct sum from 0 to the dimension of V of zonoids in the kth exterior power of V. Look at this object. So, for instance, if V is R, so what we have here is just R, R. Because zonoids on the real line, so centered segments on the real line, they're just parameterized by just one number. Now we take formal differences of positive numbers, you just get R back again. But as soon as this is of dimension at least 2, then this becomes more complicated. It's R, then there is the zonoids in R2, and then there is R again. But what I just said is that zonoids R2 are precisely centrally symmetric convex bodies. So it's a huge space, very large space. It's finite dimensional only in the case when V is dimension 1. Okay, here is the thing. It is possible to endow this object with a ring structure. So if I take an element in the say, 8th piece, and another element in the bth piece, you can define one element, which we denoted this way, A wedge B, which belongs to the A plus B piece. And you should think of this element as a sort of like a convex body analog of the wedge of differential forms. So this is a convex body analog of the wedge of forms. Okay, that's why we use this notation with the wedge. But one thing which is interesting is that this ring structure turns this into an algebra which is commutative. So the ring is commutative. Okay? It's a bit misleading because this is usually associated to skew commutative operation, but it's commutative. And it has some nice properties, this ring structure. So here is an interesting one. So if you take, for example, K1, Kn, so these are zonoids, so special convex bodies in Rn. I take n many of them in Rn, and I take their product. Okay? So, well, first of all, for each of them, the power A, so the grading is 1. So this should belong, from what I said, to the lambda nth exterior algebra of Rn, which is just R. Okay, this is where it should be contained. And this turns out to be a segment of length, the mixed volume of these bodies. Okay, this is something which is nice in this ring. Okay, so maybe otherwise it's a bit maybe too mysterious, this construction. Let me just explain what is happening here. See, this is the crucial observation that if you have a bunch of vector spaces and you have a multilinear map between vector spaces, so you see these vector spaces, each of them embeds into the set of zonoids. Just take a vector and correspond, so it is a vector, take the corresponding segment. Okay, so every vector, it's a segment in particular, so it's like if this product also somehow embeds in the space of zonoids. And the thing is that there is a unique way to extend this map to a map U tilde, which is Minkowski multilinear and continuous. Okay, so this is the thing. So for instance, if you take mu to be the determinant, which is a multilinear map between Rn times Rn to the reals, its extension to zonoids is mixed volume. Okay, so that's a thing. Okay, so this is where it's coming from. So there is some construction here. And this construction allows to define, for instance, also the tensor product of two zonoids. And whatever operation which is somehow like coming from something multilinear, you can build it using this map. And that's quite an interesting remark, because this operation at the level of convex bodies is not clear how to do it in a continuous way. So if you want to define tensor product of convex bodies in such a way that this operation becomes continuous, that's not possible actually. You cannot define a map on the set of convex bodies, this tensor product map, which is continuous. But you can do it if you have zonoids. Okay, so it's a good class of bodies in which work with. Okay, so what do we do with this? So here is the crucial thing.
So you take zonotopes because you embed the vectors this way? What do you do?
For this construction,
No,
for the top one, for the definition, for now, I mean, I'm just saying that zonoids are the Minkowski, the out of closure of zonotopes. And I'm just telling you something which is, for the moment, completely unrelated with the top blackboard, with the original problem. I'm just telling you something, some story. On the set of these zonoids, you can do this stuff. Okay? It's so there is no reason at this point why. Okay? Maybe one reason which seems to suggest that we should look at zonoids, it is that in the probabilistic Schubert calculus problem, the body that we got up there, it's a zonoid. It's a tensor product of balls. Okay? So that's just a hint. But this is the construction. So we have this ring structure on the set of zonoids. So it's a commutative graded algebra, okay, which has some properties. And this comes from this abstract construction. But now here is the crucial thing. So let now M be some homogeneous space.
So you will not define the wedge product?
Of zonoid, I didn't, sorry. The wedge product is defined by taking the unique Minkowski multilinear extension of the wedge product at the level of vector spaces. Okay? Same way as the tensor product is defined by the unique Minkowski multilinear extension of a tensor product. Okay? So there is some, but the definition of this ring structure, it's in this black box that I didn't explain. I agree. I just wanted to say that in some sense, this construction is related to multilinearity. Okay? Where you have to work with multilinearity with respect to Minkowski sum in one sense and with respect to the vector space in the other. And you have to fit these two things together through this black box. Yes?
When you have two honest zonoids,
Yeah.
then you take wedge product.
It's a zonoid.
It's a zonoid.
Yeah, so one property which is out of this construction is that if you start with the two elements which are honest zonoids, so like really convex body, not formal differences, take the product, you get an honest zonoid, so not a formal difference, okay? And there is more, so this construction is monotone, there is something, okay? But let's not get into this. Let me just explain you what happens now. If you take a compact homogeneous space, and take for V this like quotient of the Lie algebras, so this is just the tangent at M. This is my space V in which I will be working, so it's an n-dimensional space. Now here is what you can do. Given omega, a submanifold of M of codimension C, you can associate a zonoid in the seed piece of your algebra. So there is a way to associate to a submanifold one of these objects. So this is like similar to taking the Poincaré dual of something in the RAM cohomology. Okay? How does it work? So for instance, if omega is a point, okay, so codimension is the top, so we are landing in the top codimension, so k of a point, from the construction that I will tell you, it's going to be 1 over the volume of M times the unit segment. Okay, so this should be contained in R. And what is the construction in general? So I'm going to tell you. So suppose that omega, just to explain, it's some sort of like manifold like this. Let me explain the case of an hypersurface, okay? So suppose omega is an hypersurface. Then at every point of this hypersurface, we have the unit normal segment. Okay, so it's an hypersurface. So it doesn't matter if it's coorientable or not, so if the normal boundary is trivial or not, but we just have the unit normal segment, which I call it maybe S of X. It's the unit normal segment. Then what we can do, using the group action, we can imagine it like these families of unit normal segments. We move it all inside V. Okay, so we can assume that like there is a group acting, so imagine like I identify all of these tangent space at different points, all with this. Of course, this involves a choice, but the construction does not depend on the choice of this identification. And then this thing here, I write it this way if you want. It's a, let me explain in a second. So it's the integral over omega, and then the integral over the stabilizer. And then you sort of average this segment over the stabilizer and over the manifold. What does it mean? Okay, I don't want to go into the precise explanation, but let me just explain. Integrals, they are limit of sums. You're all familiar with this. Like an integral is it's a limit of a Riemann sum. So what I'm doing here, actually, I'm taking limits of some Minkowski sums of segments. That's what we're doing. Okay, so this is the construction. And now here is the theorem that if you pick a bunch now of submanifolds of codimension with the sum of the codimensions, which is the dimension of the manifold, so that you expect them to intersect transversely, you can do the product of these corresponding objects, and what you get is a number, which I will tell you in a second, times the one corresponding to a point, and this number, so precisely the same as was happening before, it's this expectation of the number of points of intersections. Where when I say these, I really mean that I move, like in the integral geometry formula, each of these submanifold independently with a copy of my group. So you see, this identity, it's the formal analog of the identities that you get in classical algebraic geometry when you do intersection theory. Let me show you an example, otherwise it's a little bit... let me show you the Edelman-Kostland-Schubs-Mail. So, example. If you take Z, which is now a random Bombieri-Weil hypersurface, I claim that omega Z, you have to do just a computation. It's square root of D divided by 2 pi times the ball. Well, then just apply the thing. So intersect, not omega of Z, sorry, this is the zonoid associated to it. Let me call this omega, not to make confusion. very hypersurface of degree d. Okay, then you have this identity. You just write the identity, and you know that this is square root of the 1 over 2 pi ball square root of the n over 2 pi ball, and this is like square root of the 1 the n times 1 over 2 pi to the n ball from one end, and on the other end this is the expectation of the number of points of common intersection times this. Now you use this property that in this ring the wedge of objects, it's a segment of length the mixed volume. You know to compute the mixed volume of balls. Okay? It's just n factorial times the volume of the ball. Just plug in this number and you compare and you get that this thing equals this. So that's, if you want, a convex body proof of this Edelman-Constant-Schubs-May. Okay. Here's another example, which is nice, that I like. So here is the example of lines in RPN meeting a bunch of subspaces, 2n minus 2 mini subspaces, each of which is an RPN minus 2. Okay, so this is like, it's another of these Schubert problems. So we are working in the Grassmannian of lines in Pn, which is like the Grassmannian of two planes in our n plus 1. I'm sampling a bunch, so 2n minus 2 many subspaces of dimension n minus 2. So for each of them, I have my corresponding omega Li. So this would be the lines hitting Li. And for those of you who know Schubert calculus, this would be the Schubert variety associated to this simplest Young diagram. And then you just ask, what is the expectation of the number of real lines eating a bunch of these random subspaces of this dimension? Well, the expectation you want to compute is, you just apply the formula, essentially. It's dimension of the Grassmannian, so what is that? 2n minus 1 factorial times the volume of some convex body. And you can explicitly write down what this convex body is. And in this case, it's again some like it's a tensor product of balls. And now when you send n to infinity, you can start looking at the shape of these bodies. And what you can prove is that this, it's something like 8 over 3 pi to the 5 over 2, 1 over square root of n, p squared over 4 to the n times 1 plus big O of n minus 1. I'm just saying that using the fact that you can write this problem as a volume problem, you can compute its asymptotic. Okay, this is so. For instance, what with Peter Burgesser we call the probabilistic Schubert calculus is nothing more than computing in the ring generated by the zonoids associated to Schubert varieties. Okay, so this is this construction. I don't want to say much more about this. I just I mean, there is way more to say, except that the feeling it is that in the same way, so maybe there is one analogy that I want to stress. If you're familiar with this like I mentioned this BKK theorem. So like when you are on a toric variety, the cohomology is generated by toric divisors. And in some sense, you can treat toric divisors using these Newton polytopes. So there is an analogy here that suggests that it's a sort of a real version of this BKK formula. Okay, so in the BKK formula, the mixed volume of some convex bodies compute some number of points of intersection. And here there is the same story happening, but over the reals for random. The idea is that this is happening in a ring. Okay, so this is the message. Okay, so let me now say a couple of words in the remaining just 20 minutes. How much I have? 25. About other non-algebraically closed fields. Okay, so far we discussed throughout this lecture with the case with R. Okay, and some of the things also can be transferred to the complex numbers, simply because the techniques fit well also over the complex numbers. But the questions, like studying the behavior of objects for which there is no generic, make sense over, in fact, every field which is not algebraically closed. And maybe I'll just spend a few words just telling you something about what happens in a non-Archimedean world. Okay, so let me just work with QP, even though everything I'm going to say holds true for every finite degree extension of QP. Okay, so first of all, what is QP? So P is a prime number. I don't know if you are familiar with this. And QP is the completion of Q with respect to a norm, which is a non-Archimedean norm, denoted this way, which is defined in such a way that the non-Archimedean norm of the ratio, say of a rational number, you do this. You write it as the ratio of two integers. You collect all the part that involves a power of p. Okay. So this has no powers of p. And then the norm is 1 over p to the alpha. Okay. So for instance, the number 2 to the n, its 2 norm, it's very small. It's 1 over 2 to the n. Okay. So the more powers of p there are in your rational number, the smaller is the number. Okay? Already from this, you see that with this metric, it's not complete space. Okay? This sequence, it's a Cauchy sequence, but it doesn't go to 0. Okay, you complete it, and you get like what is called QP. Okay? It turns out that it is a field of characteristic 0, and it's an extension of this of the rationals. And what is nice is that this norm extends, of course, to this field and turns it into a locally compact topological group. So if you take this QP, this thing, it's a locally compact topological group. The unit ball, for instance, it's denoted this way, ZP. So that's the closure of the integers under this. It's a completion of the integers with respect to this norm. This is the unit ball. Because it's a locally compact topological group, you can put a Haar measure on it, which I denoted by mu, and we normalize it so that it's 1. Okay, so we normalize, so mu is the R measure on QP, normalized such that on ZP it takes value 1. And you can do all sort of like constructions. You can define QPPN, that's the p-adic projective space. This also carries some uniform measure in the same way as we did it like for the real projective space. You can consider the p-adic Grassmannian. Okay, you can do all the type of construction. So in this game, for instance, the analog of the orthogonal group is the group of invertible transformations with coefficients in ZP. Okay, this is the analog of the orthogonal group. In which sense, so if you take QP now and you take it to the power n, that's a vector space. You can put like the product norm, so it becomes a metric space, and this is precisely the set of linear isometries of this space, this GL and ZP. Okay, same way as like it was happening with the orthogonal group. Okay, so far there is no problem with like randomness and genericity. But here is the starting example.
How you put metric on the...
Just we take the product metric in this case. You can do other things, but it's customary to take the... So, see, if you look at polynomials with coefficients in the integers and of degree d, that's just a z p to the d plus 1. That's the usual story. But here is an example. Take d equals 3, which already motivates everything. So this space writes as a union of this joint union, if you want, it's a space of coefficients, of 3 spaces. This is where there is precisely one root in QP to the polynomial. This is where there is, no roots, I apologize. This is one root, this is 2 roots, and this is 3 roots. Okay? So you see, this space, now this is a subset of Z p to the 4th. If you put R measure on this, you can ask about the size of these sets. Okay? And this has a positive size. This has positive size. This has size 0, and this has positive size. See, there are polynomials of degree 3 over QP, which have no 0 in QP, but if you perturb a little bit the coefficients, you still have no 0 in QP. And this one, it's 0 because if you have 2 zeros, you also have the other one. Okay, so this has to, in some sense, what I wanted to explain in this blackboard, it is that as differently from what happens over the real numbers, this has also some positive measure. But whatever, it's a non-algebraically closed field, so it makes sense to ask all the type of questions we have asked in the previous lectures in this field. So what is which one of these chambers is larger? What is the expectation of the number of zeros over QP? Okay, all these type of questions, you can formulate it here. And what would this question mean? They would mean, so if I want to, for instance, to compute the expectation as before of the number of zeros in QP of your polynomial, which I now should call it f. This will just mean integrate on the space of coefficients this function number of zeros with respect to some measure. Okay, that's good. Huh? So here is the point. What is the measure? So you can think about this question, but what type of measure should we take? Turns out that if you are interested for the analog of Schubert problems, like there is a unique measure on the Grassmannian which is invariant under the action of this group of transformations. But on the space of polynomials, again, something different can happen. But what you can prove it is that if the prime is large enough, so at least larger than the degree, there exists a unique, let me call it uniform measure, which is GLNZP invariant. Okay, so if you take a large prime, we are closer to the complex algebraic geometry regime, where in some sense there is only one reasonable choice for your probability distribution. But just to explain what does this mean, so you see I have the space of coefficients, and I need to somehow choose a measure on this space of coefficients, and I want it to be of that type. So like when I'm sort of the measure is supported on some lattice. So the uniform measure, that means that it's supported on a lattice. And here you have to look at it's a little bit different from the complex case. You don't have to, it's not enough to use representation theory at the level of lattices, because you still have Schur lemma, but it doesn't tell you anything about this lattice, because there are no eigenvalues that you can deal with. But there is a unique invariant one. Maybe I should use this blackboard. So the choice of the probability measure, if you want, it's dictated by good sense, okay? Common sense. And what is this unique one? Well, it's this one where you write a polynomial f, as a sum of some coefficients, x0, alpha 0, xn, alpha n, with now the coefficients which are uniform in ZP. Okay? So it's, in the real case, we would do like a Gaussian coefficient times some basis element. Here we are taking the basis element times some uniform coefficient in ZP. So in some sense, your space, after you fix this basis, you identified with like a ZP to some power, and you just take the uniform measure on this ZP to some power. Okay? So let me tell you a little bit of history of the non-Archimedean. So the first one to study this non-Archimedean problem was Evans. Who, on the space of polynomials of degree d, okay, so it worked with the non-homogeneous case, but it's the same. He put the uniform measure, but with respect to this basis. So I mean, he identified the space of polynomials through to ZP to the d plus 1 using the map that sends the coefficient with respect to this basis. And he proved that the expectation of the number of zeros here in QP, it's, there is a nice formula, p to the integer part of log b divided by 1 plus p minus 1. Okay? Which is a nice result. So he did this using this cut-slice technique, which I didn't tell you what it is. But there is something about this result, which is that this measure is not invariant. So this measure here is not invariant. So somehow it doesn't have, at least from my point of view, a geometric meaning if you pass to projective space. So it's not, it would be like it's the analog of working, like in our case for the real, and taking Gaussians in front of the standard monomial basis. It would give a reasonable probability distribution, but it's not invariant by orthogonal change of variables. So there is a bias in the zero set towards some direction in projective space. This is also something that this measure has. But you see, if you think a little bit back about how we proved the theorems, the Edelman-Kosterlitz-Schubs-Mail theorem, for instance, there was this Veronese embedding idea. Okay? And we combined that Veronese embedding idea with the integral geometry idea. So there was a way, the Veronese was translating the geometry of hypersurfaces into the geometry of like images of the Veronese with an hyperplane. And then the computation just reduced in computing the volume of the Veronese. That was the final computation using the integral geometry. And the good thing about the story here, it is that you can define a notion of volume of some algebraic set in the p-adic projective space. And this has been done by, actually, I think maybe by Serre first. Yeah, I think I think there should be a -1 probably here. There should be not many roots on it. This should go to 0, right? Yeah. 1 over p minus 1. This goes to 1. Well, when p becomes large or when degree becomes large. No, it's correct. Sorry, Shogata. No, it's correct. This was correct. So the D large asymptotic means, okay, fine. So we're going to have more and more zeros. But what is the problem? Yeah, you're right. I think I am now confused. Because a minus, I think it's too fast. But let me put a minus for the moment. Okay, let me check. So what I wanted to explain is that there is a notion of volume that was defined by Serre. So essentially, if this is codimension A, you just take the limit as m goes to infinity of p to the m and then codimension, so n minus a, that's the codimension, times the measure of an epsilon neighborhood. Okay? So this would be precisely what we are doing over the reals. We have a submanifold. What is the volume? So we take an epsilon neighborhood. Okay? And if it's a codimension C, we just have to take the volume of this epsilon neighborhood and divide by epsilon to the codimension, volume of the ball of radius epsilon dimension C, take the limit, and this converges to this. And in this case, this converges to something, which is the volume of A, which, by the way, is the same as the Hausdorff measure. But what is interesting is that with this definition of volume, there exists an integral geometry formula. Maybe I'll just say what it's true. There exists an integral geometry formula which works like this. So if you integrate on now not the orthogonal group but GLN. It's exactly the same formula that we had over the reals or the complex, but by changing everything to p-adic. Okay, so, and you can, so this was shown by myself with Avi Kulkarni. And you can just take, I mean, all the ideas that we discussed in the previous lectures, and you can export into this word, and in the end, it just reduces to compute the volume of the Veronese variety, which, this is sort of like a little miracle happening, turns out to be 1. So the volume of the Veronese variety in this basis, the standard monomial basis, turns out to be 1. So in the real case was square root of d to the power n. In the complex case was a d to the n. In this case, it's just 1. You can export these ideas also for this probabilistic Schubert calculus. We don't have a ring structure, but many things extends. You can do all sort of like computations, all sort of business also in these words. As soon as like you got the message that the real world and the complex world, these computations have to deal with like measuring and just averaging and integrals, you can do the same over these things. Okay, there is much more to say, so time is over, so I'll be happy to answer questions if there are.